this is the lecture for Friday, March 13th. We are continuing our discussion of the weak interactions. We have already discussed this slide, but I wanted to just back up to the expression for the transition rate from Fermi's golden rule. We had this factor of the amplitudes squared for the transition from the final to the initial, from the initial to the final, and this phase space factor here. Okay, and we wrote that out in terms of these nuclear wave functions, this amplitude squared for the nuclear wave functions, in terms of this Fermi function that we discussed here, and as well as various kinematic factors. Now, so we already talked about the Ketrin experiment, so let's now skip to where we want to start this lecture. So if we make the assumption that the nuclear matrix element, meaning this guy here, is relatively insensitive to the small variations in the energy, see the energy range for this beta decay is on the order of about 1 mega electron volts. If the amplitude is not changing very much in that region, and typically you would think not, then you can make the approximation that the half-life, this T1/2 times this factor f is, so the factor f is the integral of the Fermi function, okay? This integral of the Fermi function is equal to the logarithm, the natural log of 2 times these factors divided by the mass of the electron to the 5th power, and this squared amplitude, squared absolute value of the matrix elements, the amplitude. Okay, this W here that we're integrating with respect to is the energy of the electron divided by the rest energy of the electron, and this W0 is the maximum possible value for the electron. That's essentially what's indicated here, about 1.2 MeV for that case. So here's what the this F constant, or this F value looks like versus W0. Okay, and you see this is actually the logarithm of F for different values of Z. So Z is the charge of the daughter nucleus. So remember, what's happening is in the beta decay we have the daughter nucleus, and then we have the electron, and there's a Coulomb interaction between these two that distorts the wave function, the outgoing wave function of these guys. And so that's where these factors, this Fermi function is coming in to describe that Coulomb repulsion, or Coulomb attraction actually in this case, with the negative and the positive. And so you can see what it is for different values of the Z, the number of protons. This is for electrons, and this is for positrons. You can see they go in opposite directions, as you might expect, because for the positrons this would be positively charged. Now, we've actually already talked about this last time, but let's review it again. From a microscopic point of view, we can talk about the beta decay as being mediated by the W- particle, or the W+, the antiparticle to the W-, as well as the Z0, the neutral boson. So if we have the beta decay from the neutron to the proton, we have a W- particle being spit out, and then we have the production of an electron and an anti-electron neutrino. All right. Now we can also have another type of interaction where we have, for example, electrons scattering off a neutrino, and here there's no loss of charge. The electron goes to an electron, so this is a neutral particle. More fundamentally, though, we can think about these processes in terms of quarks. So we already discussed this last time, but let's just review. So we can think about the down quark converting into an up quark. So here is the vertex that's making this all happen. So from the point of view of this diagram from a microscopic point of view, we did this last time as well. We can think of the neutron as being an up quark, a down quark, and a down quark at the simplest level, and the proton is up quark, 2 up quarks and a down quark. And so what you can see is that the one down quark gets converted into an up quark it shoots off a W minus that produces the electron and the anti-electron neutrino. So what's going on here, sort of the primitive or the fundamental vertex, is the conversion of the down quark to an up quark, and spitting out the W minus particle. By the way, the charge of a down quark is minus 1/3. The charge of an up quark is plus 2/3. So if you want to just see that the charges make sense, if we have a neutron, that's an up quark and two down quarks, we have a plus 2/3, we have a minus 1/3, and we have a minus 1/3. That sums up to 0, which is neutral, which is what you expect for a neutron. For a proton with two up quarks and a down quark, you have a plus 2/3, a plus 2/3, minus 1/3, that's equal to plus 1, as you expect for a proton. Okay, so now you can then also have interactions of this kind, where we have the muon spitting out a W minus particle and becoming a muon neutrino, and then this W minus does the same thing again and produces then an electron and an anti-electron neutrino. Okay. So now there are more things that the weak interactions can do, and it turns out there are 3 copies of all of these things we've been discussing. These are called generations. So we have the up quarks and the down quarks. These are the lightest quarks, and we have the electron, neutrino, and electron. And so the electron is the lightest lepton. So remember, the leptons are these guys that don't interact through the strong interactions. The quarks are the pieces that give you the hadrons that interact through these strong interactions. Okay, so we have the up quark, the down quark, the electron, neutrino, and the electron. But it turns out there are heavier copies of all these particles. So the tron quark has the same charge as the up quark, just seems to have a larger mass. The strange quark, again, has the same charge as the down quark, but has a larger mass. Now, we actually don't know which one's heavier for the masses of the neutrinos, but all the neutrinos have rather small masses. But the muon has a larger mass than the electron, but for all intents and purposes looks like an electron. Now, there's also then a third generation. We have a top quark that's like an up quark and a tron quark, but even heavier in mass, and the bottom quark, which is even heavier than the down, the strange, and then the tau neutrino, and the tau, which is heavier than the electron and the muon. So now, what's interesting is that the weak interaction can connect the up quark not just with a down quark, but also with a strange quark. So then we can have a process where we have a particle, something like a K minus meson, which is a strange quark with an anti-up quark. This guy can decay into, so what will happen here, the pi 0 has a piece that looks like an up quark and an anti-up quark. So the strange quark can decay into an up quark and shoot off a E minus electron and a electron antineutrino. Okay. Now, how do we know that there are not more than 3 generations? That's actually a good question. There have been measurements of the properties of this Z0 particle that we just described. There have been measurements of it's an unstable particle because it can decay into pair particle and antiparticle, particle-antiparticle pair, and you can actually measure the production of neutrino and antineutrino for the various types, for the electron, for the muon, and for the tau, and these decays will make a contribution to the width of the Z0 resonance. So remember, we talked about these unstable particles and these decays and decay width. Okay, so they can measure the width of the Z0 particle, and they see this as some sort of like a bump in the cross section, and the width of this bump is proportional to the width of the decay width of the particle. And by measuring the width of this bump, you can actually make a very clean prediction of how many neutrinos that the pair of neutrino-antineutrinos that the Z0 particle can decay into. And the result is that to a very high certainty, there are only 3 pairs of neutrinos that the Z0 can decay into, suggesting that there are only suggesting there are no extra generations of neutrinos that couple to the Z0 with any significant strength. Now, this, for some people, for a lot of people, suggests that there are only 3 generations, and this is because of the fact that with each of these generations, the mass of neutrinos end up being very, very small, well below the mass of the Z0 particle, which is, we mentioned before, was on the order of about 90 gigaelectron volts. And so the expectation is if there was a 4th generation, the neutrino that was associated with that would be below the Z0 mass, and it could decay into an extra pair of neutrinos, and that has not been observed. And so that is actually, for most people, pretty strong evidence there are not more generations of these particles. However, it's not an airtight case, because you can imagine that perhaps the neutrinos were heavier than the Z0. Okay, we talked about, though, this possibility that the strange quark can couple to the up quark. So you can think of this as some sort of mixing process. In other words, you can think about the weak interactions couples together the up with the down. So we have this diagram. The up and the down quarks are coupled together with the vertex that involves the W minus particle, or the W plus particle, okay? But now you can think about the down quark as perhaps the up quark and the down quark, somehow this down quark somehow gets twisted around so that it actually decides that it actually wants to be a linear combination of a down quark and a strange quark, okay? Now, why would that happen? Well, first of all, I said that the strange quark is like another copy of the down quark, just having a larger mass. What's going on here is that through the weak interactions, there's a coupling of the up quark with something that has the characteristics of a down quark, maybe called a down prime, but it may be that this thing that the up quark couples to through the weak interactions is not a mass eigenstate. In other words, it actually couples to some linear combination of down with strange, or maybe even a little bit of a mixture of a bottom quark. Okay. Now that sounds kind of crazy. Why would it want to do that? But the reason this actually does happen, and in fact it does happen, it's been observed very many times, we know this to be a fact, there's something called a Higgs particle. And this Higgs particle couples to quarks and leptons. And it's actually this coupling, if I have, let's say, a down quark like this, there's a coupling of the Higgs particle to these states, these quarks and leptons. And it turns out that this Higgs particle can couple to not only the down quark, it can couple to the strange quark, all of them. Okay. And what happens is that this Higgs particle plays a very special role in nature, in that it kind of gets stuck, meaning that there's a potential that looks something like this. For here's the potential as a function of the value, the average value of phi, and what happens is that it loses some symmetry. In other words, if it weren't for this potential, the average value of phi would be centered around phi equals to 0, but it actually ends up that the potential has a relative maximum at phi equals to 0, and so the minimum value is actually at a non-zero value of phi. And this is something called spontaneous symmetry breaking. What happens is that the average value of phi is actually a non-zero value. And so because of that spontaneous symmetry breaking, what happens is that these down quarks and up strange quarks get all mixed up in terms of their propagation. They get a little bit confused, if you like. And so as a result, the up doesn't just couple to down, but it couples to down and strange and bottom. Okay? So one way of saying is that there are these strong interaction quark mass eigenstates, up, down, charm, strange, top, bottom. But then these are different from the weak interaction eigenstates. So there's some sort of misalignment of what the strong interactions want to do for the masses and what the weak interactions want to do, so that the up quark actually couples to the down prime, the charm couples to the strange prime, and the top couples to the bottom prime. Okay. Now, so as a result, we can then think about how this mixing occurs. Now, I should mention this angle here, theta c, is what's called the Cabibel angle. So it's a relatively small number, 13 degrees. So if you plug that in, it's not that large. So there's a little bit of mixture, and the generalization of this mixing is to a 3x3 matrix is what's called the Cabibel-Kobayashi-Maskawa matrix. Okay, where we have these mass eigenstates, things that have well-defined mass. They would propagate, and you could say this guy has this mass, this guy has this mass, this guy has this mass. But the states that couple through the weak interactions are mixtures of these mass eigenstates, and so we have then these matrix elements, what are called the CKM matrix elements for Cabibel-Kobayashi-Maskawa. Okay, UUD is the coupling from the the first generation, coupling to okay, so the coupling from the U to the D, the coupling of the U to the S, coupling of the U to the B, and so on. Okay, so you can see numerically what these values are. This is about 1, this is also about 1, this is also very close to 1. So it's very close to the identity matrix, but there are non-trivial, non-zero values on the off diagonals that produce this mixing. Okay. Now, this matrix here, in order to preserve probabilities in the quantum mechanical amplitude measurement, this is a unitary matrix, meaning that the matrix, the U dagger, must equal to the inverse of U. We've discussed unitary matrices. And so this matrix here, if you put in the various, these are just absolute values, but you put in the minus signs and the phases, complex phases, this should be a unitary matrix. Now let's talk specifically though about the transition between an up quark and a down quark, the UUD term. So that will involve this term, the Cabibel angle here that we talked about. And so there's this coupling that involves the Fermi constant for the 4 Fermi interaction, as well as this Cabibel angle. We'll come back to that later. Now let's talk a little bit about helicity. So helicity is the amount of spin that you measure for a particle, dotted with the unit vector pointing in the direction of motion. So if I have, so suppose a particle is going this way, then what I'm doing is I'm measuring, so I take my z-axis is to be in the direction of the motion. So this would be what I call a positive helicity, and this one would be a negative helicity with the right hand and the left hand. Okay. Now, if the particle is going the opposite direction, then I would take that direction to be the positive z and measure. This would be positive, this would be negative. All right. So we can talk about h greater than 0 as being right-handed. So as I said, this way, or I can have it this way, being left-handed, the helicity. So positive is right-handed, -1 is left-handed. All right. And now the question is what is going on with the helicities and the neutrinos? And it was observed that the neutrinos that were being produced in various weak interaction events were almost always, well, they were always coming out as being measured left-handed, whereas the antineutrinos were coming out right-handed. So how could that possibly be? Well, the coupling of the coupling of the W particles and the Z particles, bosons, to the leptons as well as the quarks are rather complicated. It turns out that it's not just simply this interaction that Fermi wrote down in the beginning, that there's actually I'm not going to go into the details of this, but there's a vector piece of the interaction, and there's an axial vector piece of the interaction. In a special combination, let's call it V minus A, meaning that you have an equal amount of vector minus an equal amount of axial vector subtracted together. And what that ends up doing is it makes the left-handed neutrinos, well, the left-handed particles, the only ones that are interacting through the weak interactions, and also the right-handed antiparticles are the only ones that are interacting through the weak interactions. So it's sort of what's called a maximal violation of parity. This, by the way, was not understood until relatively recently, well, in the 50s, that parity was even broken. But the point here is that there's what's called a maximal violation of parity, where there's an equal amount of vector and axial vector piece to the interaction. The fact that the axial piece is there at all was a surprise, but the fact that it was as big as the vector part was a big surprise. Okay? So anyways, we can talk about the coupling of the axial vector. So remember, axial vector refers to something like angular momentum, right? So r is a vector, p is a vector, but when we do r cross p, we get another thing that looks like a vector, but has the funny properties under parity. So that's what we think of as an axial vector. Okay, so this axial vector coupling for the weak interactions corresponds with something called GA for axial vector, and then there's a vector coupling called just GV. And the ratio of these two is what's called small GA. We just call it GA. And there's a prediction that in the limit that the quark masses go to 0, that you can relate this ratio in terms of the decay constant of the pion. This thing's called the Goldberger-Tremont relation. It's related to the product of the decay constant for the pion times the coupling of the pion and the nucleon divided by the mass of the nucleon times c squared. I realize I'm just pulling this out of a hat. This takes quite a bit of effort to prove, but this is in the limit that the masses of the quarks go to 0, it turns out that the pions end up becoming massless, and there's a whole bunch of things you can prove in that what's called chiral quark limit, and one of these results is this Goldberger-Tremont relation. Now experimentally, the value of GA is 1.267 plus minus 0.004, and this is very close to within 3% of this estimate from the Goldberger-Tremont relation. Now, let's talk about the weak nuclear interaction. So I was talking about the vector part and the axial vector part. But let me try to give you some sense of what the difference is between the two. Okay. Now, here is then what's called the Fermi interaction, and so this guy carries 0 angular momentum, and this is coming from the vector part of the interaction. Okay. So what this vector part of interaction does is very simple. It basically just has a tau plus or minus operator here. So tau is for isospin. So what exactly is going on here is, so this plus or minus, this is, for example, tau x plus I tau y, that's the plus, and then tau minus is this guy. Okay. So these are just changing from protons to neutrons. It's sort of going from proton to neutron or neutron to proton. And then whatever you do on this side, you do the opposite thing on the other side, because you see the plus goes with minus, the minus goes with plus. So this is just changing the isospin for the nucleons, and then you do the same kind of thing for the leptons, but here you would convert electrons to neutrinos and vice versa. Now for the axial vector piece, it's pretty much the same thing in terms of the isospin and the lepton sector here, but there's an additional piece that you have the spin of the nucleon is involved, and there's a dot product between the spin operators here. Okay, so this is what's called a Gamow-Teller interaction, and it's a bit more complicated, but it's not that much more complicated. You just have that the spins of the nucleons are involved. What is kind of interesting is that the Fermi interaction, this vector part interaction, is really, really simple. So in particular, if you have states, if you have various states, initial states, final states of the, where, let me back up a second. If the initial state and the final state of a decay through a Fermi interaction have the same, belong to the same isospin family, so in other words, they're connected to each other by isospin, then the matrix element of this guy is actually something you can calculate just on a, there's an exact result for it, essentially. There's no nuclear structure involved here, okay? It's something you know a priori. Whereas the Gamow-Teller transition does involve a spin flip, so there's a change in the nuclear wave function. And so that then requires knowing a lot more about what's going on with the nuclear physics. Okay, but the simplicity, absolute simplicity of the Fermi interaction, this vector part of the interaction, means that you can predict exactly what this should be without knowing anything about the nuclear structure. And that is enough to actually make a prediction about what is this Cabibbo angle, and what are the elements, in particular this VUD element here. It gives you prediction of this guy. So that's actually the best way to measure this VUD parameter through something that's called super loud Fermi beta decay. So the term super loud means that the initial state and the final state, these guys are connected to each other by isospin. They belong to the same isospin family. For example, just doing an isospin rotation of a neutron to a proton goes from the initial state to the final state. So that's what's been done, measuring these super loud 0+ to 0+ beta decays between various t equals 1, that's isospin 1 multiplet analog states. These are states that belong in, the states, as I said, are in the same isospin family. So you can, as I said, you can make a nice prediction for the Ft value. So remember, T is the half-life, F is this Fermi function, this integrated Fermi function. And so you can make then a prediction of what this should be, and you can see the prediction is really quite accurate. Notice the numbers here. It is really right on top of the data for various different nuclei. As I said, these super loud Fermi decays are insensitive to the nuclear structure, and so that can be used to make a prediction for VUD. In fact, the VUD squared value here is about 0.949 if you square VUD with rather small errors. Now, because we said that the Kobayashi-Maskawa matrix was a unitary matrix, that means that every row, if I take this row here, if I take the square absolute value of this plus the square absolute value of this plus the square absolute value of that, that must equal to 1 in order for this condition to work. If you're not clear on why that works, you just simply take the Hermitian conjugate here. You take the Hermitian conjugate, I get the adjoint of the star of UUD, I get the star of UUS, okay, and star of UUE, and you go through and you just do the multiplication, and you see that you get this constraint that the VUD squared plus VUS squared plus VUB squared will give you, must be equal to 1. So you can check this, what's called the CKM unitarity condition. And so you can get the VUD from the nuclear decays. You can also get it from muon decay if you want. But then for the others, you need to go to other systems, like from kaon decays, the decay of a kaon meson, which we were talking about. Those are the strange mesons, the ones involving the strange things, like we talked about the K minus was a strange quark with a K minus with a strange quark with a U bar, anti-up quark, and that gives a value of VUS squared of about 0.05. And for the B meson decays, so that's involving things like BU bar, okay, and that would be a B minus meson, a much heavier meson. And from that you can get the VUB squared, and that's a very small value, turns out. And the unitarity condition works well, suggesting that we perhaps have a good description of what's going on with the weak interactions in the standard model, which is kind of impressive.